Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future, preparing for the exam. Today we are going to start a new part about query languages. It will have a focus on trees because we've been looking a lot at XML, JSON, at about denormalized data and the like. But many of the design patterns that I'm going to show you actually apply to all data shapes. So it's very important to understand what characterizes a good query language, what are the components of a query language in terms of design, what's the difference between a draft and a fully specified query language. We look at the implementation and a lot of different aspects. So let's get started. So you see we are almost arriving to the end of the semester. We've built the whole stack almost. We know how to store data in HDFS, in S3, in Azure, blob storage. We know how to encode, even though that was very quick. We know syntax, CSV for tables, XML, JSON, YAML for trees. There's many others for other shapes. Then we have the data model where we saw that XML and JSON is actually a tree. When you parse XML or JSON, then you get a tree in the memory of the machine. And this tree is going to be validated potentially with schema languages that we've studied a few weeks ago, like JSON schema, XML schema, JSON, which allows you to optimize the tree because then you can store data with the actual types that it has. Then we can process it. So we saw the first generation of large-scale processing with MapReduce. We saw the newer generation of a framework with Apache Spark. There's a few others, but really they are very similar to each other. We saw that there's data lakes, but there's also the traditional approach where the data is hidden, where we have full data independence, and we have a system like PostgreSQL or like MongoDB that exposes the data model and hides the rest to the user. In that kind of system, there's a lot of more features that come with these systems. One of them is indices, because indices allow you to make queries much faster. In Spark, you would have had to scan the entire data set. Of course, it's in parallel, so it's efficient. But when you have an ETL-based system that indexes the data, then you can actually get answers within milliseconds to questions over looking up something in a collection of billions of different records, just a few milliseconds for a lookup, for example. We saw that PostgreSQL, of course, and many others for SQL, IBM, Oracle, and Microsoft are the big three. There's a few open source ones like MySQL and so on. We saw that for trees, there's a whole ecosystem as well with MongoDB, ExistDB, MarkLogic, Couchbase, and so on, specifically designed with denormalized data, so document stores. Document stores are more recent. So unlike, we actually saw that unlike PostgreSQL, MySQL, and so on, who all have SQL as a query language, they have a query language, document stores do not all have a query language. All of them have an API, and some of them have a query language. And we are en route to a future where also the denormalized data, also at large scale, should ideally become fully data independent, just like PostgreSQL. So hopefully we'll get ACID, we'll get updates, we'll get everything and a completely hidden and abstracted layer below. But you see, this is what's been going on for 20 years. That continues to go on. In the lecture last week by Bart Samuel, you saw that this is exactly what Databricks is working on. I imagine Snowflake as well. They are trying to turn the data lake into a database system that seems just like PostgreSQL and the others, where everything is smooth and data independent. All right, so this is where we are, and today I'm going to be focusing on the query languages. So a few more words on data independence and why it's important. You see here, logically, so that's a SQL query. Physically, you could be using PostgreSQL that actually writes the data on disk and uses the CPU of the machines. But what's very, very powerful about SQL as a query language and generally query languages designed with that in mind is that you can swap the physical layer. You could use Hype running on MapReduce. It's the same language. It's still SQL. Or you could use Phoenix, Apache Phoenix running on Apache HBase, the one with the white column store we've seen a couple of weeks ago. The same. It's SQL again. Same language. or you could use Apache Spark. We also saw that Apache Spark has SQL, Spark SQL, that runs on data frames. Inside, below, there is also an API. So very often you have a query language and below an API. We saw that this is what it looks like with RDDs, because eventually, physically, it's implemented with RDDs. But we also have a data frame API that you can use as well, right? But the end user, at the very top, they get a fancy, shiny query language that hides all of the complexity, and we can just swap this physical layer. So now we saw that that was for tables. So SQL was designed for tables, and we saw that over the decades, we've accumulated a lot of data sets that don't actually fit in tables. They don't fit in tables for various reasons. It's the real world. This is real world data. You can change the schema of the data over time when you accumulate it over 20 years. So these are numerous reasons. And so you end up with extra values, with missing values, with values of different types within the same column. You end up with nested tables in there, all kinds of nested structures. So we are in the world of denormalized data, nested, heterogeneous data sets. And we know that these are, in fact, collections of trees, exactly. These are collections of trees. This is the model that we use to model such data. If the trees are not too nested and not too homogeneous, you can still abuse tables, so push it into data frames and so on, and still view it like some fancy tables. But when it starts to be really nested and heterogeneous, then you might as well change the logical model and just accept that you're actually looking at collections of trees, which makes things much easier and more understandable for the end user. So we saw, I spent some time at the end of the data frames showing you the limits when you try to import a data set. In that case, domain integrity is broken, as well as relational integrity, and in fact also table integrity. They're all broken. What happens is that Spark still fits it in the system, but it just turned everything into a string until now, whenever you had domain integrity broken. More recently, as of Spark 4, which was very recently released, we have the variant type, which also exists, I think, in Snowflake and other systems. It's better, because at least you acknowledge that you have typed data in there. It's not just a string, but you've only pushed the problem further to the user. You still, if you have to query this with SQL, it's still not straightforward in some cases. And so to illustrate that I wanted to show you examples. So for example, this is Spark SQL with lateral views. You remember that lateral views are there when you have nested tables inside the tables, and you want to put it in first normal form, actually. You have nested data, and you want to normalize it into the first normal form. The way you do that is that you take every row of the nested structure and you duplicate everything that's outside, and you end up with a table, right? So this is what the lateral views are doing. It can be seen as some sort of a join between the table and its nested table. You can also see it in that way, that in a way, the lateral view is some sort of join of the table with the nested tables, right? For whom is that intuitive, right? So this is the idea of lateral views. So of course, if it's not too nested and so on, you can go ahead and use this, works perfectly well. But there are cases in which you will have queries that with lateral views and so on are going to be looking more like this, right? In that case, I think what we are doing is that we are looking at GitHub events, and we are looking for the commits by the top committer of the event. And in a language that was designed for trees, this is what it looks like. It's just a couple of lines, 6 lines here. But in a language that was designed for tables and that you try to use with trees, then you end up with something more complex. So the query on the right was written by Ingo Müller, who was the previous head TA of the course. You can imagine what he had to go through in order to write this. So this is on a data set that's known as the GitHub archive data set, which we use actually at the exam. It's a data set that looks like this at the top level. Of course, it's just an excerpt. What's interesting about this data set is that even though for every event there's less than 100 attributes, the total distinct number of attributes over the entire data set is above 1,000, just because it's very heterogeneous. You have attributes in some of them, but not all of them, and so on. And in fact, 10% of the paths on here have mixed type. If you look closer, you will see that this actually happens inside an object that's called payload. Inside the event. And specifically, this nested object is the one that causes all the heterogeneity, and that in older system, you would have to either force into a string to make it work, which is what I think BigQuery was doing when they were processing this data set. That is the way it's documented. So this is a concrete example of data set where you're hitting the limits of what SQL can do. So I'm going to show you and drive you through a query language, JSONiq, because I co-designed it. It was also one of the early ones 15 years ago. Now there's 30 of them, right? So this is the reality. It didn't get standardized, even though this one is actually, to a large extent, a W3C standard. This is just real life. Hopefully it will consolidate in the coming years. There will be also an industry standard. But for now, it's not the case. So I'm going to teach you this one. And all the features that it has, I'm going to talk on the high level, are actually common to the other languages, right? So if you know this one, then it shouldn't be difficult at all to learn any of the other languages, right? And I'm going to focus on the design of the language, a lot more than in previous years, because I redid almost the entire lecture this year, because I put the tutorial for you in the early weeks. Who actually did the tutorial now? Well, a couple of raised hands, very nice. If you haven't, please do it. It's a very good idea to do it because it's used at the exam, JSONiq. So I'm going to tell you on the high level some of the distinguishing features of a NoSQL language, of a tree-based language. But some of them, again, also apply to graphs, to cubes, and others. JSONiq works, in the case of Rumble, on top of Spark. It runs on top of MongoDB also. I added a MongoDB collection function for you, so you can also use it on MongoDB. PostgreSQL also. Basically, it runs pretty much on anything where you can store trees directly or indirectly, right? So this is the idea. And in fact, when you have a language that runs on many platforms, that's also the case of SQL, of course, you can also talk about federated database systems or data virtualization. It means that you access with the same query multiple systems. You could, for example, do a join between MongoDB and PostgreSQL, right? Which previously was not really possible because of data silos, right? If the data is in different systems, you can't really put it together. But with modern database systems, you can actually query across silos, across systems with a unified language like this. All right. So these are a few of the languages out there. Every couple of months, there's an announcement that a new company figured out that they need a query language for trees and creates a new one. So there's maybe the most popular, or at least those that got viral, Uncle, Particle, I think was by Amazon, Xqueries for XML. This one is the standard for XML. GraphQL by Meta, even though this one is not actually a real query language, it's more like a subset of the functionality. And unlike the name indicates, it's for trees, not for graphs, but it communicates the idea that you have the structure. We have a SQL++ that extends SQL, but not in the way of Spark SQL, in other ways to also try to make it work on trees. AQL, which actually means the Arango, there's even collisions now because so many languages. So the Asterix query language, the ArangoDB query language, Miracle, and so on and so on and so on. Right? So this is the landscape, but really, if you look at the features, they have a lot in common. We just hope it will consolidate someday. But I'm confident because for graphs, we actually achieved consolidation very recently, just 1 or 2 years ago. And now we do have a standard for graph databases. But I'll talk about that in next week, actually, I think. So RumbleDB is the engine that we use in the course. It works on S3, on HDFS, on HTTP. You can also directly download over HTTP datasets. The local file system, it can be on Azure, on Google Cloud, so wherever you want. Even I could have added now PostgreSQL, MongoDB, and so on. So a lot of different storage. It supports text, JSON, XML, CSV, Avro, Parquet, Root, libsvm, and so on. And the idea is that JSONiq could be seen as the ideal lakehouse language. So the lakehouse was this new concept that mixes a data lake with a warehouse into a single integrated system. And so this is the goal of the overall vision that we have. RumbleDB was actually built by your predecessor. So we have more and more every year. So now we have Matteo and Omar who are writing their projects with me. But you see also all the previous students and PhD students and postdocs who contributed to it. So this is really an ETH effort with a lot of people at ETH, and we keep building and developing the system further. So it's for the students by the students. Now, I'm going to start looking into the aspects of JSONiq, but in fact, like many other languages, and I really would like to emphasize on the high level. Maybe some of you will participate in the design of languages or the modification of languages or updates to languages because there's versions, right? Every couple of years we add features. So what I would like to emphasize that is very important is that if you have a query language, it manipulates something. Maybe it's trees, maybe it's tables, maybe it's cubes, maybe it's graph, but it manipulates something. And so you need a data model. You need a specification or a document that describes what you are manipulating. And what they look like and what are their properties, and accessors is also a technical word. So it's a data model that says what the language manipulates. Then we have the expressions. The expressions are the Lego bricks. That's why it's called data bricks, probably. So the Lego bricks of the language, right? But unlike transformations, which you could also see as bricks, right in Spark, the expressions are not in an API. They are more like in a context-free grammar, like the sort of grammar you would build with NTLR. Who took a compiler course? Right, so many of you. So this is what I mean with expressions. These are really non-terminals in a context-free grammar, if you want to imagine them. Then we have, in any language, a function library. I will also say a few words about that. You cannot make everything an expression, because if you end up with 1,000 expressions, then you can forget it. The people are not going to learn the language. So typically, I would say the order of magnitudes in the number of expressions in a language is maybe 30, 40, 50. That's a good number. Everything that goes beyond, in terms of features, you should expose it as a function, right? And typically, you can have functions libraries with hundreds, 200, and more functions in there. They are just not full expressions because you need to call a function. And in order to decide if something is an expression or a function, that depends, is it used a lot? How convenient does it make it to have it as an expression rather than a function? But this is the idea. So you have a huge function library in every language. Then you have the schema validation language that is also part of the system. In SQL, it forces you to validate from the beginning. So in that case, the schema validation language would be the create stable statement in SQL, right? Now we see that in that case, we have JSON, XML schema, JSON schema but it's still the same idea that we validate data, except that now it's optional to validate it, whereas for tables, it was mandatory to validate it before. So this is one of the things that changed. Then we have the parsing and serialization specification. Parsing is how you parse the data from some syntax or binary to the memory. Typically, it's part of the data model. So when you define the data model, you also have some documents that tell you how the syntax is mapped to the data model. The serialization is the other way. It's when you have an instance of the data model in memory, how do you convert it into text or binary on this? This is called serialization. And that's also, I will show you an example, but this is also something that is defined on its own in a modular way. And then you have a test suite. A test suite is a lot of tests that you run so that implementations can implement it. To give you an example, the test suite for xQuery by the W3C has 30,000 tests that implementations need to run, and then you have a dashboard that tells you how much of the language you cover. This is important for interoperability, that you have standards, because then you can reuse the programs across different systems. But the lesson here is that it's modular, so you will have different specifications: a specification for the data model, a specification for the expressions, specification for the function library, specifications for the schemas, specifications for the serialization, the test suite, which is not, well, it has a spec too that explains how it works, but the test suite, the main important part is the actual tests and the expected results. Who is with me? Right? So this is a message to you. If you update or create new query languages, you really need to keep in mind that it's a whole ecosystem of specifications. It cannot be just a quick draft with a few examples. You really, really need to specify everything correctly. And to give you an idea, we always underestimate the time it takes to design a language. A language like xQuery took, I would say, 20 years plus of work by 20 plus people meeting every week for 2 hours over the phone. Back then it was a conference bridge over the phone, but just like we would use Zoom today. So just to give you an idea of the actual workload of designing a language, because when you design a language, you need to design every single corner of every expression. You have to think of every single particular case that can pop up and agree on the language. And so typically, I was in the working group at W3C for xQuery, and there was people from IBM, people from Oracle, people from Microsoft. Everybody had implementations or prototypes or their own proprietary implementation. And then you meet in order to discuss how you agree on some common ground based on a consensus to design all of this. Right? So this is the atmosphere. All right. Okay. So I'm going to have this in mind for the whole lecture, these categories that I gave to you, and I'm going to start with the data model. Right? So the JSONiq data model says, what does JSONiq manipulate? The answer is simple. It manipulates sequences of items. This is the one automatic answer that you can give to that question, sequences of items. So I need to tell you what the items are. So what do we have? That should not be surprising, actually, because it's based originally on the JSON data model. So we have structured items like objects and arrays, right? So it's not surprising that we can have items that are objects and items that are arrays. Then we have the atomic items, which bear a type. So we have strings, numbers, booleans, nulls, dates, and many, many, many others that I showed you many times on my slides. So something like 25 or 30 different standardized types. And then we have XML node items, even though it's not the focus, and we are not going to do that during the exam, so you don't have to program with this. But it also has element nodes, attribute nodes, text nodes, and so on, so that you can also manipulate XML data. Right? So with the same language, you can manipulate JSON and XML. Everything that is in there except the null, which is specific to JSON, everything that is in there and that is in there is W3C standard. So that's the xQuery and XPath data model called XDM. The function items, we also do not cover them too much, and we don't ask you to master them at the exam. It's just that you can also have items that are functions. So you can have sequences of functions. You can call them dynamically. You can define them dynamically. It's actually very useful for machine learning. There was a very nice master's thesis a couple of years ago where we did use function items to manipulate machine learning models that you train, that you test, and so on. Right. So this is also a W3C standard. And objects and arrays are specific to JSONiq, but they were also eventually standardized into xQuery, and we are in the middle of aligning them to the latest version of xQuery that also gives a standard for objects and arrays. All right, so these are the items. Who is with me? Right, so every one of these things is an item. Now, the items are like elephants. They are not alone. They live in groups and they live in sequences. And so this is why we always have sequences of items, not just one, but many. So what's important is that a sequence of one item is the same as that item. It makes things easier. So if I say a sequence of one string item, that's the same as saying it's a string item. Or if I say an object, it's the same thing as saying there is a sequence of one object. If I say a query returns an object, it's the same as saying the query returns a sequence of one object, right? You just see them pop up on your screen. It's just that there's only one, right? Who is with me? Right? So it's a mathematical trick that I think mathematicians call it an injection. You basically inject that set canonically into this other set of sequences. A sequence can be empty. It just means that it's possible to return nothing, right? That's just the empty sequence. It has absolutely nothing. And then sequences, of course, scale, but they do not nest, right? You never have a sequence in a sequence. Whenever you try to put a sequence in a sequence, it's always flat, always flattened, right? So they scale in that way precisely because you don't have to nest them in this way. To billions, trillions, and more, you can really have sequences of billions of items. This is how RumbleDB was implemented to have items in such large numbers. I insist that what I'm saying here is that sequences don't nest. Sequences are flat, but sequences are not the same as arrays. You could have sequences of arrays, and then when you have arrays, you can have arrays of arrays, objects of arrays, and so on, right? So it's just the sequence that is the outermost thing that you can have, the one that you can have billions of. And just to give you an intuition of why it cannot nest, imagine if you were trying to nest a sequence of 1 billion items inside an object as a value, right? Implementing that would be a bit tricky, right? So because of this limitation, I told you that typically a document store limits the size of a single item on a record or an object or a document to 10 or 16 megabytes. The number of values you can have in the arrays is not as large as those you can have in a sequence. So the sequences are really these absolutely huge things that you have on the outermost level that are flat and that do not nest. Who is with me? Right? Okay. We'll see that in fact we are going to implement the sequences with RDDs and data frames in Spark, right? But I'm keeping that a bit for later. So the sequences of items were designed in such a way to be flexible in the sense that a sequence of items can be structured. Here it's a sequence of integers. Here it's a sequence of Booleans. Here it's a sequence of objects that are all valid against the same well-behaved schema. Who agrees it's a table? Right. You see, that's what I wanted as part of the course to see that this is actually a table. And then you can have more heterogeneous aspects like arrays of various sizes, and you can have also completely heterogeneous sequences. In that case, it's a sequence of 4 items, an integer, a Boolean, an object, and an array. And it's a perfectly fine sequence to take or return by an expression. So you see that it covers the whole spectrum now between fully structured data and unstructured data or semi-structured data, as we call it. And also, a sequence can have a single item or be empty, right? So here it's not even a table, it's just a single value. These, of course, we are not going to bother implementing as RDDs or on top of Spark. We just directly process them locally. But that, again, is a physical detail that you don't need to care of when you learn the language, right? Okay, and the sequences of items, again, that's a W3C standard. Right? Who is with me? Right, so let's continue. I'm actually done with the data model. So now, if I ask you the question, what is the data model of JSONiq? What does every expression take and return? You tell me. Sequences of items, exactly. So that's the idea. So now let's go to the second part, where we are looking now at the building blocks of the actual language, the expressions of the language. There's around 30, I think 37 last time I counted, but of course it can evolve with time. And an expression takes or return a sequence of items, exactly. So you see always, 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 which is an instance of the model. So you have an expression, takes sequences of items, returns one sequence of items. That's the the simple way of putting it. It takes sequences of items, returns sequences of items. once you start implementing it, you realize it's slightly more complicated than saying that. So I did a slide for those of you who are interested, and otherwise just forget about it again. What actually happens when you have an expression that contains sub-expressions. Imagine, for example, if you have 2 times 4 plus 1, then you have a multiplication nested in an addition, right? You agree with that? So this is what I mean here, that it's a sub-expression within an expression. What happens is that an expression could be complex, could be your whole program, actually, your whole query, always takes a dynamic context. What do we have in the dynamic context? It's the variable assignments. For example, I could have an expression that is $x plus 1, so the variable x plus 1. My context is going to tell me the value of $x for this specific evaluation is 3. And then you evaluate $x plus 1 as 4, 3 plus 1. But that's because you had the context. If I don't give you the context, and there's variables in there, then you cannot evaluate it. So you always need a context to evaluate the expressions. I'm not going to bother you with everything there is in the dynamic context, also fully specified by the W3C standard, but I don't want to scare you. So the simplest thing you can think of is there's at least the variable bindings. So eventually, the expression has to return a sequence of items, but in order to do so, it has to evaluate the sub-expressions, possibly multiple times. There are cases where you need to do it multiple times. I will show you a few examples. And in order to evaluate these sub-expressions, oh, I'm disapparating and apparating now. Strange, okay. So in order to evaluate these sub-expressions here, multiple times, you need to build a dynamic context. In some cases, it's the same that you just forward, but in some other cases, you need to add some variable bindings that depends on which expression you're talking about, right? Every expression is different. The same here. And every time you pass a dynamic context to the sub-expression, it gives you a sequence. Maybe you do it a second time with another context, a third time with another context, but basically you get sequences. The same here. You could even have 3, 4, 5, 6 sub-expressions, right? It also scales that way. And then you get sequences, and then you combine these sequences into a result sequence. How it's combined, again, depends on the expressions. For each one of the 37 expressions is going to be different, right? An example, and here I'm getting back to the simplified notation with just the sequences. So when I show this slide here, sequences, I mean that part of the graph here, right? So with plus, if I have the expression 1 plus 1, then that gets me 2. So it's a sequence of one item, 1, and also another sequence of one item, 1 on the left and on the right. And then I get out of that a sequence of one item, 2. Right? That's an example. It could also be that the expression was $x plus $y with a context that says x is 1 and y is 1. But eventually you get this 1 and this 1 out of the evaluation of the sub-expressions, and then you return 2. Who is with me? Very good. Here's another example where I have, some of you already know if you did the tutorial. Imagine you have a lookup. The lookup means $x dot foo, let's say, $x dot foo. So on the left, you have $x. Let's say that this is $x. It's a sequence of 4 objects, in fact, flat and homogeneous. So that's actually a table. So it's $x dot foo. So you have this sequence of 4 objects, this sequence of 1 string. And out of that, you get the sequence of 4 integers, 1, 2, 3, 4, because they come from here. And again, that's because this expression here tells you that the semantics of that expression say you're supposed to find out the key with this name right here and extract the values in there. Who is with me? Right? And so that's what the specification says. For every one of these expressions, it explains the behavior that it has, including all the corner cases. You can actually look at the spec. Maybe I can share it on the course material. You will see how long it is and incredibly verbose, and we call it species, the language, right? So the specification language, it's very, very long. And in fact, the people who are supposed to read this, they are not the end users, they are the implementers, right? So the end users, they will buy books or they will look at tutorials over the internet, but the specification is important for the implementers of the language who builds the actual engines, right? So my students have to look at the spec, for example, my students who do projects on RumbleDB. Okay, so that's an object lookup. And in the end, it's like a Lego game. Who plays Lego? Right, so it's the same. You basically build a huge Lego construction. You just use expressions instead of Lego pieces. But it's exactly that same idea. And so in all, what we have is some sort of data calculator where you enter an expression in there, except that this expression might be more complex than just plus, multiplication, division, and subtraction, right? Just more than that. And it returns always a sequence of items, exactly. In that case, 3 objects. It's actually a table with 1 column that you see right here with 3 records. Okay. So then I insist that the idea of the Lego game, and that's what makes it a functional language, an expression, any expression can be the operand of any other expressions. It might be that you need to add parentheses, of course, right, in order to make it work, but potentially with parentheses, you can put an expression inside any other expression. Now, of course, when I'm telling you that, I'm not saying there won't be an error. For example, if you put a string inside an addition, that's not going to work. Right? Because the string can be concatenated, but I know in some languages they use plus for concatenations, but not in SQL and JSONiq. In SQL and JSONiq, it's the double vertical bar, right? But basically, syntactically, you can put any expression in any expression, and it will at least make it past the context-free grammar and the parser in terms of your query. Any error would be output later in the pipeline of evaluation. Okay, who is still with me? Right? It's the first time I'm trying it like this, because the previous years it was more like a JSONiq tutorial for 2 hours, and then I thought maybe it's a bit boring, and so I completely changed it to explain in a more abstract and hopefully interesting level. So just to show you an example, this is a Lego construction with expressions, and really to give you the idea, we have this 2 plus 2 that evaluates to, you're following, right? 4. Then we have the dot B. You see the dot B extracts the array here. Then we have this magical, I will come back to it, it's called array unboxing, that opens the array to a sequence. So here it's a sequence of 1 object, so that's it. Then this dot A gives us 4. Then 1 plus 4 gives us 5. And 5 to 50, 2 is also an expression that returns a range. So it's the sequence of all the integers between 5 and 50. And that's what we get. That was the evaluation. Basically, the job of the evaluation is the engine. The engine is supposed to evaluate it. But since it's a functional language, the engine can do absolutely what it wants as long as it gives you the correct results. It means it can completely ignore some parts of the queries that it figured out have no effect on the results. It can use lazy evaluation and so on. It can parallelize. It can do whatever it wants as long as the results are correct. That's the beauty of a functional language. Okay. Now a trick in the grammar, you know, when you were in the compiler course, that when you design your context-free grammar with the non-terminals and the terminals, that creates precedence rules between the expressions. And typically what happened is that in the when you're almost at the end of your hierarchy of expressions, then you have this double parenthesis, and you put inside that the top-level non-terminal. Who has ever seen that? You should have seen that often in grammars. It's exactly the same way that it's done in this language. So it means that I actually don't know the precedence of the expressions. I have an intuition maybe for some of them. For example, I know that multiplication has precedence over addition, but I must admit I'm a human being, I don't know the precedence. So what do? I just put parentheses whenever I don't know. And at least I'm sure that the order of evaluation will be as I figured out. So I don't really expect you to know beyond some intuition, these precedences. I don't know it. I don't know it by heart. Again, just put parentheses. It's magic. Whenever you have them, you know that it's going to force nesting the expression. Now, it's a bit like the Spark lecture where I gave you a lot of transformations, but again, I shortened it a lot. I would like to give you the high-level categorization. You know that when you play Lego, you also have these categories of pieces, right? You have the ones that are like blocks, you have the ones that are flat, you have, if you play, I don't know if it's called Lego Technique also in English, but you have these wheels and all kinds of things, so you can categorize them. Well, actually here it's the same. We have categories. So the easy category that everybody knows very early is arithmetics, comparison, logic, string concatenation. There's always an example on the right there. Then there's the data flow. It has if, then, else, switch, type switch, try catch, and so on. So that's anything that is known as control flow in other languages. But here I'm saying data flow because actually it's the data. Word of warning, this if then else in here would not correspond to the if then else of Python or Java or C++. It would correspond to the ternary expression with the question mark and the colon. Who has ever seen that? Right, many of you. This is what it corresponds to, because the ternary expression with the question mark and the colon is the actual functional if then else. Right? And so what it says here is if $A, then $B, else $C. And in fact, in Python, it will only evaluate the sides that corresponds to the truth value of the predicate, $A. But in fact, since it's a functional language, you could evaluate both $B and $C and $A in parallel, all three of them. And then, depending on the value of $A, you pick the results from $B or $C. Right. I think it's even used in, I think it even led to a security issue in hardware. I think not too long ago, there was precisely because the hardware was eagerly evaluating some expressions, and it led to some issues, but that has to do with side effects, because it's very hard to do when there are side effects. But here it's a functional language. There are no side effects at all. So it's totally safe to evaluate $B or $C because you're just calculating things. Right. So who's with me? Very good. All right, so what's the third one? Dynamic functions, you can forget them. We are not going to use them in this lecture. Maybe I could also have added the function calls in there. So obviously you can call a function, but this is done in the same way as in many languages, just with the name of the function and parentheses, right? But the dynamic functions, the function items, is the same. You don't need to worry about them. That's absolutely not part of the lecture. Then you have the object array, nodes, values, and so on. I'm going to show them to you, but again, it's intuitive, right? It resembles JSON. We have the variables. They start with $, right? I'll explain why also. Navigation and filtering, I have a few slides about that. That's a super important feature of NoSQL languages. Flower expressions, also super important. It's like the select from where for these languages. And then type expressions like instance of, cast, castable, and so on, right? So this is the menu of expressions. You should really do the tutorials, make yourself familiar with these expressions, and you will see there's actually not too many of them, right? So just to show a few, I'll pass because it's very easy. The first thing you need to know is you can copy-paste any JSON into JSONiq. Always works. It's just going to return itself, right? It's very, very intuitive. So even that, in the bottom right, that is a JSONiq query that returns precisely this, so a sequence of one array item. But it's dynamic. In that case, it's not dynamic, it's just something that returns itself, right? But I told you it's a Lego game. So inside of that, you can also put expressions. For example, you could have something that looks like an object. Here, there's a function call. Here, there's an array, but inside the array, you dynamically iterate and build a sequence of longs. And that gets you this result at the end, a sequence of one object. Who is with me? Right. So it's like JSON, but you generalize it. It's some sort of dynamic JSON where you can add expressions instead of the keys and instead of the values. You can also do it with the keys, not just the values. Okay. Is it out of batteries? Don't know. Yep. Also, the casts is like function calls. So to casts, to dates, long, short, it, long, and so on. You just call a function on putting an item that needs to be converted. Right? It can be a string, but can also be from another type. This shouldn't cause any problem. The list that you see here should not be new to you. It's the same list of types that I gave you many times in JSON and XML and JSON schema and XML schema, right? It's the same one. For whom is that not new? Right? It's exactly the same list that I've shown previously. All right. And sequences, finally, can also be built manually with commas. Just put a comma, and you separate all your values with, like, this is a sequence that's going to return a sequence with one array, one Boolean, one string, and one object. But again, that can be expressions instead of the actual values. All right. I think we deserved a break, so I'll let you with this. That's the easy part, right? You just copy-paste JSON, but it also is a bit dynamic. That's the idea. So let's go for a break, 15 minutes. and then I'll continue at 3:15. Thank you very much.